So virtual memory is something we need to discuss in operating systems. It's basically the way the operating system is going to map the memory of your program into its system. So when you're writing a program, it's from your point of view, your program starts at location 0 and goes until it ends. But the operating system is going to take that, it might cut it up into little pieces and scatter it throughout your operating system. And it has to keep track of where everything is. So this is a definition off of Wikipedia of what a virtual address space is. And so you could read this. And basically, this is, maybe I'll go through an example and you get the idea of what the point of this is. So, let's say for example, you wrote a manuscript for a book that you would like to get published, and the manuscript is 965 lines long. So you send that to a publisher. The publisher wants to turn it into a book, and the publisher makes a decision. This is completely independent of you. The publisher makes a decision that the pages of the book will have 50 lines each. They could decide 40 lines, 60 lines, it's up to them. But they decided, because they're the ones handling your book, that the pages have 50 lines each. So suppose after the book has been printed, you wanted to find a line that is, say, line 965 in your manuscript. Where would that be in your book? So how would you figure out where that is? The first step is you'd have to figure out what page you're looking for, right? You'd have to know how big the pages are. So you would take 965 divided by the size of a page, round that number down, and you'd realize you're on page 19, right? And then you would take the line you're looking for and do a modulo on 50, divide away all the full pages and just take what the remainder is, and the remainder would be 15. So the line you're looking for, which is in your mind is at 965, line 965 in your manuscript, is actually in the book on page 19, and it's 15 lines down from page 19. Does that address translation make sense? Okay, so this is kind of the idea. We're going to be doing basically this concept. You write a program in Java, you compile it and save it on the hard drive. In your mind, it starts at 0 and goes until it ends. The concept of some book publisher or somebody taking that and chopping it up into pages and then you have to find where stuff is really not an issue with you when you're compiling. But the operating system is going to do that. So for example, you could put a file out on your disk drive. So this will be process A. Process A is from the point of view of the person who made process A. This is just one long continuous like the manuscript. It's just your program starts here, and if your program says go to this area or calls a function and the function is located here, you're just jumping here. The idea of this being broken up into pages is something you didn't take into account when you made this. But when it gets copied into the operating system, like the book publisher, will cut it up into pages. And they're going to do something more interesting than the book publisher. The book publisher prints the pages, and the pages are all one after another. In an operating system, they may take these pages and then just stick them in spots in memory that happen to be available at the moment. So for example, process A, which is made up of 4 what the operating system is going to call equally sized pages, could find itself in a situation where page 1 is in memory, page 2 is currently not in memory, page 3 is located over here, and page 4 is located over here. Now the question is, we need some kind of like index to know where the stuff is. So if you want to make a reference to page, let's say page 1 is currently running, which means we're processing out of this storage. If this now calls a function that is in page 3, we have to take a timeout and figure out where page 3 is. Then once we know where page 3 is, then jump to page 3. So how do we do that? We'll have some kind of a table that says, well, page 1 is here, page 2 is missing, it's not in memory. If we actually needed page 2, we'd have to go out to the disk drive and bring it in and then add a pointer to it. But right now, page 2 is not available. Page 3 is located over here, and page 4 is located over here. So if some code is running here and makes a reference to page 3, the operating system has to say, okay, we have to calculate where is page 3. Well, we calculate how far away this is trying to get to, then realize that belongs in page 3, very similar to the calculation we just did with the book a second ago. We go up to this table and find out where page 3 is, and then go here and then say how far into the page we are, and that's the location we would want to go to. So here's a diagram of just how the computation, like we had just done with the manuscript getting turned into a book, we're going to for 2 reasons. Not because it makes the math easier, but actually because if you remember from hardware, it's very easy to transfer data if you transfer it in blocks that are of powers of 2. So transferring 8 bits or 16 bits or 32 bits is very easy because you could just transfer them across a bus with that many lines to it. So what we're going to do in an operating system, whenever we choose a page size for a process, we will always choose the number of bytes to a page to be a perfect power of 2. So the offset, like in our manuscript example, the offset was 15. You remember 15 lines into the page? The offset will always be a perfect number of bits, which actually makes things very easy. That modulo operation we did with the book and the manuscript, we don't have to do that. We would just copy the bits directly down. So for example, if we wanted to go to page 3, the bits, so this would be now what we're going to call a virtual address, and this is going to be called a real address, where it's really located. So the virtual address might be, like in the manuscript example, line 965, and the real address will be page 19, line 15. So that's what we're trying to do in this case. So we're basically saying if we wanted to go to page 3, let's say back on this previous example, if we wanted to get, let's say we were processing out of here, page 1, and this made a reference that was 32 bytes into page 3, the virtual address would be page 3. It would be 000000011, right? Because 11 in binary is 3. And then how far into the page is whatever these bytes are. So we would know we're looking for page 3. So we don't go to this address. We take page 3 and pass that into the beginning of our address table, which tells us that, here would be page 0, 1, 2, and 3. So here would be the address to page 3, where page 3 is. And that will tell us where it starts, so that gets to be the high-end bits of the real address, which would end up being, it would be like taking that manuscript thing and getting to page 19. And then how far into the page we go, we just copy those bits directly down. And we could do this using hardware. The copy of these bits directly down is a bus. And then we could use, if you remember from hardware, we could use like a translation look-aside buffer to get these bits to map directly into here. In other words, all the bits in this table can run into a big OR gate, and depending on which page number is here, would let one of those sets of bits flow right here. So the address translation is done very quickly with hardware. Okay, so does this make sense? That we're going from this address is from the point of view of your program starts at 0 and goes to wherever it ends. This address is where the chunk you're looking at the moment happens to be residing in main memory. We could go a step further and have like a segmented paging system. In other words, your program could be so big that you take your program, cut it up into segments, which are variable in size, and then within each of those segments you can chop those up into equally sized pages. So all that really does is add another layer onto the page translation. So basically, let's say segment 1 has 5 pages and segment 3 has 10 pages and so on. We'll basically take our address and allow a certain number of bits to be the offset, how far into the page you go. Then which page number for that particular segment you are, we'll dedicate a fixed number of bits for those. And then another set of bits for which segment you're in. So depending on which segment you're in, you go to your segment table, and that tells you this is a list of all your segments. And then whatever the segment number is, it's that many units after the beginning of the segment table. And that'll tell us the address of that particular segment's page table. So really, this picture should have had one segment table and many of these. I should have drawn like to say that there's many page tables. Each segment has its own page table. So now we're taking the address of a particular segment, adding that to the page number, and that tells us where the page table begins, or how far into the page table is, and then the number there gets copied in as the real address. So this would be for very large programs that you want to just do more than just having a paging table. Okay, so then fragmentation ends up being the amount of, the amount of space, I don't want to say wasted because it's necessary, but the amount of space used up just to do all this bookkeeping. So for example, the first example where I said, let's say you wrote a book, and that was maybe 1,965 lines long, and every page is 50 lines. Well, the last page had 35 blank lines, right? Like if you opened up the book and went to the last page, it would be the first 15 lines would be used and the last 35 would be wasted. So you're wasting some page space there. And then we also have to have all this table space to keep track of where the pages are. So I don't want to call it wasted space. Yeah, this is from Wikipedia. It's not wasted. I kind of don't like that, but it's the amount of data it's metadata. It's data about the data. So it's the amount of data that we have to use or waste just to implement this system. So we don't want the fragmentation to be too large. We'd like to somehow minimize that. So if we made the page size too small, we wouldn't have a lot of waste, because if the pages were really small, well then the very last page, the waste on the end would be extremely small. If we made the page sizes really big, we're going to have a lot of expected waste on the last page. But then because the pages are so big, the size of our tables get small. So it's kind of somewhere between the two is the low point. And so we could use calculus if our goal was ever, not that operating systems really care about this, but if our goal was to pick the best page size to minimize the amount of fragmentation, just a little model like this, we could just say S is the segment size, P is the page size, E is the size of the entry within a page table. So this is it's not wasted space, we need this space, but it's space we have to use in the main memory to run this system. And then capital F would be the amount of fragmentation. So we want to minimize capital F. So the amount of the percentage of our segment, for our whole segment, how much data we have to take up just to run this paging virtual address translation system. It's the number of page entries divided times the page entry size. That's the amount of space we're going to have. So it's page tables times, it's the number of entries in the page table times the number of bits we use to put the address in. And then we want to also add the amount of wasted space on the last page, and then divide that whole thing by the segment size. So the percentage of fragmentation ends up being this equation, which you just clean up the math and you get E over P plus P over 2S. So just a little refresher in calculus, you can take a derivative to find a relative maximum or relative minimum, and in that case we had a relative minimum. So if our goal was to find the page size, which makes our segment have the least amount of fragmentation, we'll just take the derivative and set it to 0, and we end up getting the page size is equal to the square root of 2 times the segment size. So for example, if a segment had 128K, this is an old example, because memory is much bigger than this, but if a segment had 128K, what would be the optimal page size to minimize fragmentation? So S is 128K, remember 1K is 124, so the best page size would be the square root of 2 times 128 times 1K, which would be 512 bytes. And then in that case, we are dedicating 0.5% of our memory to just managing our memory, which means 99.5% of our memory would be dedicated to the actual storage. So just as like a little example, the operating system almost all operating systems pick a page size and stick with it, because their hardware moves pages from the disk drive into main memory based on a fixed size of the buses. But if your operating system had the ability to dynamically change these, then it could become interesting. It could change these numbers and bring in bigger blocks, which are going to then have bigger wasted space. But the movement of bigger blocks could cause the number of times you have a page fault to reduce. So just to go through some examples, if we dedicated A bits to the address, to the segment number, B bits to the page number within that segment, and C bits to how far into that page we go, and did an address translation. If we did this, so you have to kind of remember this. So we had the virtual address is A bits for the segment, B for the page within the segment, and C would be the offset. The number of entries in the segment table would be 2 to the D, and then the real address page would be E bits. So some of the questions we could ask is like, how many bytes are in a page? Okay, and I got the answers up here in red, but how many bytes are in a page? So if the page can be addressed with C bits, right? Like if you had 3 bits, it could be, 0 through 7 bytes in that page. So whatever 2 to the offset is would be the number of bytes in a page. How many bytes are in a real address? The real machine address, not the virtual one, not from the point of view of the programmer, but from the point of view of the actual machine that's loaded into. Well, what happens is with this translation is these virtual addresses go through a translation mechanism and then eventually says we have E bits for the real page number and C bits for the offset into that page. So that would be E plus C. Let's see. What is the maximum number of pages allowed in the system? Pages allowed in the system. So that would be, well, actually, the question should have said the number of pages allowed for a particular segment. So this would end up being however many bits are for A, that would be the number of segments that we could go to, and then therefore that each segment can have 1 page table. So the number of page tables allowed in the system, I should have said allowed for that process. And then the maximum number of pages allowed for within a segment. For any individual segment, the number of bits in B, or actually it should be 2 to the B, would be the number of pages that we can have. Yeah, 2 to the B. Okay. And then how many pages in main memory are dedicated to some processes segments? So that's the number of bits for both A and B together. So A and B together, the bits of A and B together, even though it's going through a 2-layer translation system, this is how many bits can be used to point to different pages. So that would be 2 to the A plus B. And then, anything else interesting? What is the range of starting addresses for the page tables? So, well, okay, this is kind of, students have said, the starting address for page tables, a lot of times the operating system starts at address 0, but I'm just saying it's from address 0 up to 2 to the D minus 1. So the location for segment for page tables could be anywhere from 0 up to 2 to the D, and I'm just saying minus 1 because we're starting at 0 and going to that number minus 1. And the virtual address space for a process. So the virtual address space is from the point of view of the person who created the file on the disk drive. They think the files start at 0 and go as big as they can go. How big can they go? Well, it's all these bits are what they're using for their address. So it would be 2 to the A plus B plus C. From the point of view of the developer, let's say you're writing Java code and you create a class file. From your point of view, your program starts at 0 and goes as far as your compiler will let it go. And then when you put it on the system, all those pages don't have to be in memory as long as the operating system does this address translate. So from the virtual point of view, it's this many bits, these are the real bits, and these are the steps for the translation. Okay, so now if we had segments, variable size segments, and this concept carries over into storing files on a disk drive too. So where would be the best place to put files? Well, one of the best places to, well, there really is no right answer. In fact, everything in an operating system is there's no right answer. There's just always what's the best at the moment. So it's good to know all the different answers that are out there. So one place to fit things, and again, these concepts reappear when we talk about disk drives later on. The best place where it fits, the first place where it fits, and then this is a little controversial, the worst place where it fits. But let's say, for example, we have a certain amount of storage. So this is storage for our whole main memory. We're going to dedicate a section of it to load the operating system in, which is going to manage all the processes that are running. And then suppose process A arrives and it's 2 pages long. So we're going to try to keep this as simple as we can. We have a very small memory, main memory. Process A is 2 pages long. So where should we put it? Well, right after the operating system, we have a whole bunch of, let's say this was initially open. So we put 2 pages for A here. Then process B comes in and takes up 3 pages. So where would you put that? Right after A? Right? Why not? The space is empty when this thing originally started. So then we put B here, here, and here. We take up 3 spaces for B. Then process C shows up, which is 1 page long. So we put it right there. Then B finishes, B completes, and the operating system frees up that space. So the space that B was in was right here. This area now becomes free. So we have process A, process C sitting here. And this part here would still be open. Then process D comes in. So now here's the interesting question. Where would you, I wish I kind of had like a JavaScript thing that this could change, each one of these lines would change, the picture would change. But if you had to put process D somewhere, and you had A here, the first 2 frames, then you had 3 open frames, and then you had C here, and then 3 more open frames, where would you put D? So you see at this point we have a choice, right? So what are the choices? We could put it in this spot, or this spot, and I guess if we pick this spot, we should put it near the top. Anybody have any other choice to put it? Actually, I think this is almost so simple you really only have those 2 choices. But would anyone, if you were designing the operating system, where would you put it? Or what would be your location to put the next segment in? Would it matter?
And the one that was just free, like at the top.
The first one that's free?
Yeah.
Okay. Okay, or would you like continue, because C was here, would you just keep continuing when you get to the bottom and then maybe start over, or does it really matter? It's probably, well, one argument would basically be start at the top and just find the first free spot where it fits. So let's say we did that. Let's say we put process D right in here, and then process E shows up, which is 3 pages long. Well, E can't fit here because there's only 2 empty spots. So we could put it down here where there's 4 empty spots. We could put it right in here and it fits. Now remember, what we talked about earlier is they don't have to actually be contiguous in a row, right? We could scatter them and then just build a table to have pointers where they are. But right now we're sticking with, it's nicer if they are contiguous. But if there's not, we'll use that paging table concept. So, and again, this is going to be true for disk drive, loading stuff on a disk drive too. So let's say after process E comes in, which is 3 pages long, we put it here. Now F comes in, which is 3 pages long. And so we have 2 blank pages here and 1 here, and if for some reason we had a rule they had to be put in the same spot, we may have hurt ourselves by putting D here instead of here. But we didn't know that was coming. We can't predict the future. We don't know what size processes are coming in the future. So the idea was basically this. We had, when D arrived, so we had A came in, B came in, C came in, and then B left, leaving 3 pages empty here and 4 pages empty here. When D showed up, we could have put it in where the 3 are, we could have put it in where the 4 is, or we could have said the first place it fits. So really, the 3 popular algorithms are the one where it fits best, that's where it like fits in with the least amount of fragmented waste at the end. The one where it's the first place we find it, that would be good because it'll get us there quicker. Right? We don't have to check everything and pick the best spot or the worst spot. We just check the first thing that hits. We put it in. The idea of the worst fit is kind of like you're trying to have a lot of small but somewhat good sized fragments around because you think future processes coming in will fit in there. But it's really debatable which of these 3 algorithms is the best. This is the fastest. This is the one that it's kind of like if you're running a restaurant and a table of 4 people show up, so you find a table that's 4 or slightly bigger and give it to them because you want to save your table for 8 in case a big group comes. So it's kind of like that idea with the best fit. And then the worst fit is the idea that, I think the way I happen to just wrote this example was the worst fit would have ended up working best. Because when D arrived, we had a segment of size 3 and a segment of size 4. If we put it in the segment of size 3, then we have 2 segments, one of size 2 and one of size 4. So we're kind of hoping a big group comes in and a little group comes in, but if 2 medium groups comes in, it might have been better if we put it there. So there really is, no right answer. It's just a matter of you're leaving it up to chance and how much work is it for the operating system to implement one of these algorithms. So the idea of page replacement is basically when a program is running and it makes a reference to a page that is currently not in memory. Obviously we have to take a time out, go out to the disk drive, find that page and bring it into memory, update our table to show that it's now in memory, and then continue processing. So that's going to take some time. So then there's the topic of local replacement and global replacement. So local would be if you're staying within your process, like let's say your process is dedicated to have 4 pages no matter what, and so if your process needs a page that's not there, you have to pick one of your 4 pages and get rid of one. Global means like the operating system can say, well, this process ate up a lot of pages and isn't doing much, so I can kick that thing out and give more pages to your process. So within your process, whether you're doing global or local replacement, there's a couple of choices when to pick which page goes to make room for the incoming one. So we could use the first come, first serve. We could use the last come, first serve, which is debatable how that. There are certain programs that kind of cater to that, but they're usually rare. First come, first serve is an easy one to implement. So let's just say, for example, your process is given, the operating system gives your process 4 pages, 4 slots in memory for your pages to come in. So your program starts running, it references the first page loads in. The second page it comes in, it'll have a free frame to load it in. The third and the fourth will load it in. And then when you go to reference a 5th page, one of the 4 that you currently have in memory, you have to kick out. I shouldn't say you, the operating system is going to pick which one of those 4 gets kicked out to make room for the page you're referencing. So of the 4 pages that are in there, the operating system has to pick one, kick it out. It doesn't really kick it out, it just writes the new page on top of it. So what starts to become interesting is the methods for picking the page that goes. So this would be a page replacement algorithm. The method for picking the page that goes, there's 2 things. The most important thing we care about is we'd like to pick the one that we're not going to be needing in the near future. That would be the best thing. Pick the page that we don't need in the near future. And the other thing is the operating system doesn't want to spend a lot of time in calculating which page to take out, because that's taking up time away from the processing. So the first in, first out, the method is to select the frame from main memory that has been in the longest and remove that one. This could be implemented with a linked list of all pages that are currently in main memory. So when a page gets loaded into memory, the operating system also has to take time to add a link, maybe say that page number, and put it on a linked list. And then we just maintain the linked list. At the end of the linked list, when we go to pick a page, we just read from the beginning of the linked list. We know the page that came in longest ago, and take that one out. So maintaining a linked list isn't too bad for an operating system to do, but somehow it has to know when it goes to pick which one gets thrown out. We have to have some kind of mechanism. For the last in, first out, if you remember from your data structures class, that's kind of like a stack. We could maintain a linked list, but it's just which end of the linked list we pick from when kicking something out. So the implementation and the cost per page replacement ends up being the same. So does anything intuitively, can you think just off the top of your head, if you had to kick a page out, what would be the best one to pick? So if you had, let's say the operating system picked a page size, so that's independent, just like when we talked about writing a manuscript. The publisher picked the size of the page. You don't pick the size of the page. So you write a program, and the operating system picks a page size to cut your program up into and move it in and out of the operating system. So if the operating system, let's say, gave you 4 page slots, and you put 4 pages in, and now a 5th page needs to come in, and out of the 4 that you currently have in memory, one of them has to go, what would be the best one to pick? If you could look into the future, even if you use magic, what's the best one to kick out?
The one that's not going to be needed for the longest time?
The longest time into the future.
Yeah.
Right. So, yeah, actually, maybe I should have put that one next. The optimal method. So the optimal method would be to look into the future at the pages that are going to be referenced in the future, and the one that's needed furthest into the future, kick that one out. The implementation for this is you have to somehow predict the future. So if the program that's running has logic in it, if then else logic, you can't predict which paths are going to be taken, especially if people are entering information to determine which way to go. So not a very not a very realistic page replacement algorithm, but once the program finished running, you would then know what would have been the best. So it could end up being the benchmark that we're going to use. Well, what's something somewhat close to, if you tried to predict the future looking at the past, right? People do that with the stock market. It doesn't always work, but if you're trying to predict the future looking at the past, what would you look at in the past?
The price?
What's that?
The price change?
The what?
The price.
Oh, for stock, you mean?
Yeah.
Yeah, okay. Well, what I'm trying to say, like, if people say, yeah, so for stock, if you want to know if a stock's going to go up, you say, well, it's been going up in the past week, therefore it should go up in the next week, but that's not always right. But if you know what pages came in, and you're keeping track of the past, and you're trying to predict the future, a popular one to be, a popular page replacement algorithm would be to take the least recently used one. Out of the 4, let's say an example of 4, the 4 that are in memory right now, the one that's been used, the one that hasn't been used for the longest amount of time might be the best one, because you think your program doesn't seem to need it more. Could be wrong. I mean, the second you kick it out, you might need it, but it's a good thing if you could look into the past and do this. So now what we'd have to do, this becomes more time consuming to implement, but probably gives a better estimate of which one we should kick out. In this case, every time in the first come, first serve, every time a page got loaded, we updated our linked list. But if a page was loaded and then never used again, it didn't affect our linked list. If a page If another page got loaded and was used heavily, it's still at the end of our linked list, so nothing changes. Here, the way we'd implement this is we would have a linked list, but every time a page not only gets loaded, but even referenced, that link has to get moved to the end of the linked list because it's now the most recent one. So the linked list will always be in the order of every time it was referenced. So now every time, to implement this, it's a good algorithm so we can kick out the best candidate page that we don't need. But now every time we touch a page, we have to manipulate this linked list. So this is a time-consuming one to implement, which is the downside, but the upside is that once we kick a page out, hopefully it's the best one to kick out. There's other ones like not used recently, which is we're trying to implement least recently used, but we don't want to spend the time of going through the linked list, finding the link, and then propagating it to the end of the linked list. That takes a lot of time, a lot of computation. So what we could do is we could have a couple of bits. We set a bit that says, like, when the page gets loaded, the bit being 0 means it hasn't been touched yet. And then if it gets touched, we can turn it to 1 and maybe have 2 or 3 bits that say each time it gets touched, we're kind of keeping a count, and then the one with the highest count stays in, and the one with the reference bit that is still set to 0 would be one to kick out. But it's kind of taking that linked list concept and turning it into a 1 or 2 or 3 bit yes or no thing. So you could have 4 pages in memory. 2 of them have the bit turned on, 2 of them have the bit turned off, and then you're just going to randomly pick one of the ones where the bit's turned off. And then there's a second chance algorithm because you're kind of falling victim to 1 bit being set to 0 because you just got loaded in. You get to stay. So there's little changes to that. So just to go over some examples, there is no right answer to these page replacement algorithms, but we're going to introduce the concept of a reference string. Let's say we have, I should have one numbered 0, but let's say we have a process that has 4 pages. And so the reference string being 1, 2, 3, 4, 3, 4, 2, 1, 3, 4 means as your program was running, it was processing out of page 1, then when it jumped to a page boundary, it jumped to page 2, then it may have processed there for a while, then jumped to page 3, then jumped to page 4. So these are actually the transitions. And so what we'll do is we'll try each of the different algorithms. If we use the first come, first serve, and our operating system, we have a 4-page program, but the operating system only gave us 3-page frames. We would, using first come, first serve, our 3 frames would be empty, and we'd start referencing the first, this is our reference string, we'd reference the first page, so we have a page full here, a page full here, and a page full here. Now we reference page 4. So we have page 1, 2, and 3 in memory, and we have to kick one out. So we decided to use first in, first out, which means 1 would go, so 4 would go into this frame. And also remember, we have a table that says 4 is located here, 2 is located here, 3 is located here, and 1 is not in memory. Now we reference 3 again, so there's no page full, because that's already in memory. We reference 4 again, so that's good news, it was already in memory. We don't have to spend the time to go out to the disk drive to get the page. And now we reference 2, which is in memory. And now we reference 1, which is not in memory. So we have to kick someone out. Now the pages that are in memory are 2, 3, and 4. 2 came in the longest time ago. So out of 2, 3, and 4, 2 would get kicked out, 1 would come in. And now we reference 3 and reference 4, which are in memory. So we have a total of 5 page faults. It's 1, 2, 3, 4, and okay, 1, 2, 3, 4, and 5. So with this particular reference string, using the particular first in, first out algorithm, we have 5 to count. Following the same thing, last in, last out, it's a difference of which of the page frames get kicked out. And this ended up having a same reference string using a different last in, first out algorithm would have 8 page faults. If we use the least recently used, which is the most time consuming because we have to maintain that linked list, and every time a page gets referenced, we move the page that was referenced to the front of the linked list. This one, for this particular reference string, ended up having 7. So what I'm kind of introducing is, it's not, this algorithm is not always better than the first come, first serve. It's expected to be better, but it's not definitely better than. And then the benchmark is the optimal algorithm. So the optimal algorithm is where we're allowed to look into the future. So if we're referencing page 1, we load page 1, then page 2, then page 3. Now we have to load page 4. So we have to pick 1, 2, or 3, which one of them to kick out. The optimal method gives us the ability to look into the future. So we look into the future. Well, the future is going to need 3, and then 4, and then 2, and then 1. So out of the 3 pages that are currently in memory, 1, 2, and 3, 1 is used most furthest into the future. So we'll kick 1 out and make room for 4. Now 3 is okay, 4 is okay, 2 is okay. Now 1 needs to be referenced. So we have to kick someone out. So we look into the future. So we're about to reference page 1, which means we're looking at these 2, 3, and 4. And then we want to look into the future. The future is going to need 3 and 4, so we'll kick out 2 and put 1 here, and then we'll go the rest of the way. And we end up having 5 page ones. So whatever algorithm we use, we couldn't possibly avoid 5 page ones. For sure we'd have that. And then the one we use, you just hope it gets as close to 5 as possible. And then the idea of the working set, we'll talk about this more when we talk about queuing theory. But the working set principle basically says when a process is running, if it hits a point where it has what we're now calling a page fault, you reference a page that's currently not in memory. So you have to go out to the disk drive and bring it into memory, update the tables, and then let the process go back to being running. The process control block for the process that's waiting for the disk drive to bring a page in gets moved on to a queue that says it's waiting for the page to be loaded. Because there's no point in running it if the page it's trying to run is not in memory. So that gets put on a wait queue, and then hopefully some other process runs. So from the point of view of the overall operating system, we would like to have the processor, and if you have many processors, have all of them, have their utilization be as high, as close to 100% as possible. So the operating system would like to have the set size of page frames for each process chosen in such a way that we have the greatest probability of having the processor running at 100% utilization, running 100% of the time. So when we get a little more into queuing theory, we'll pick up on this example. But the point we're getting at is this. We don't want every process to be given 5 frames, some fixed number of frames. Like every process gets 10 frames and that's it. Because, first of all, a process that only has 8 pages, we shouldn't give it 10 frames because you're just wasting 2 frames. But the size of the frames that you get should go up and down based on the utilization of the CPUs. And so that'll be a part of the operating system, which is generally called the performance monitoring part of it. Will determine the size of how many page frames your process gets while it's running. So anyway, I know I went through a lot of stuff quickly. I kind of went over really what's considered 2 operating systems topics, but they overlap, obviously. So one is virtual memory, how to map your pages into memory and keep track of them. And then the other one is a topic called page replacement, which is when you have to kick one out to bring in a new one. Which one do you kick out? So, any questions on these topics? Okay.